Let me welcome everyone to the this particular session. So, on behalf of Lewis Stokes Midway's Regional Center of Excellence, we welcome you to today's session. This is Top 25 Orals Group 4. Before I introduce today's speaker, I would tell you that I am Dr. Monica Frazier. I am director of the Southwest Georgia LSMP Alliance. I am at Columbus State University in Columbus, Georgia. So this session is being recorded. It will be made available for viewing through the WOVA app by next Wednesday. Please provide any feedback you have about the sessions in a survey whenever you have an opportunity. I will ask that if you have any questions for the presenter, that you please put them into the chat. And then after the conclusion of the session, the presentation, I will then ask those questions on your behalf to the speaker so that they can answer those questions. This session is scheduled to take place, it will to be 1 hour, and each person has at least 5 minutes with a couple minutes of question and answer. So at this point, I will go ahead and introduce our first speaker. So Jonathan is coming to us from County College of Morris.
Represent New Jersey. Alrighty, so
All right,
I can start whenever.
Yes, you can go ahead.
Right. Sounds good. All right, hello everyone. My name is Jonathan Granda-Caro, and today I'll be presenting Studying Electric Fields, Effect on Reducing PM 2.5 Pollution. Now you may be wondering, what is PM 2.5? Well, PM 2.5 is particulate matter, which are mainly carbon particles that are less than 2.5 micrometers. These particles come from mainly from industrial pollution and have negative impacts on both just the public health and the environment. Currently, there are many electrostatic air filters based on the following mechanism, which would basically apply a strong electric field and through incoming polluter air, and then let these particles be ionized, which are turned into little sparks and then are turned into ash and are caught. And this is like right here, we have a typical industrial electrostatic air filter. And currently, these machines, can't really capture PM 2.5 because carbon particles are very, very tough to ionize, and they're very small. So to really kind of counteract this, there have been many carbon filters added, but mainly carbon filters can't really handle high temperature or airflow. And it doesn't make sense for a factory to really have those on because they produce both. And then moving on to the experiment, since PM 2.5, these particles can't be ionized, Dr. Tao and his laboratory have developed a new electrorheology approach, which lets these particles be not ionized, but rather polarized, which now then are electromagnetically attracted to electrodes, as shown here, and then are caught, and they're prevented from going off into the air. And then the machine that was created by Dr. Tao and his laboratory that was utilized in this study is shown right here. You can see it's kind of a little hard to see, but it includes a power supply, a chimney, high voltage creator, voltmeter, electrode capacitor, and a metal funnel, as you can see. And then we'll just move on to the experiment here. So to study the effects of electrorheology and reducing, to study the effects of electric field on reducing PM 2.5, 6 samples were created to really see what are the effects of this, which were at 0, 6, 7.25, 8.5, and 9.75, and 11 kilovolts per centimeter. All these samples were looked at 800 times magnification, and these were some of the tools that were used to analyze, which are microscope, Nikon microscope, microscopy camera, and ImageJ software. And for these test samples that were made, we were allowed 20 minutes of smoke particles to pass through our high voltage electrodes and into a glass slide. And now moving on to the samples with varied voltages. As you can see here, we have 6 samples we've created, and we have different images of each sample according to the voltage that was applied. And then to analyze these samples, we used as mentioned before, microscopy software, ImageJ, and we used its measuring capabilities and counting capabilities. As you can see, we're able to count all those small particles that were present after each sample, or the yellow tick marks here. And we did that for all samples. Now moving on to the results and analysis, as you can see from the table here, at the beginning of the experiment, we had 163 particles present, and then towards the end, after we applied 11 kilovolts per centimeter, there were over 4 particles present. So based on these results, there was a 97.5% decrease in PM2.5, which is a strong evidence that Dr. Talent's laboratory's electroradiology approach is very effective. And once upon graphing all this data we collected, we were able to see, as seen in graph here, graph 1, that there was an inverse relationship between the voltage and the number of particles remaining. As you can see, as the voltage increases, the number of particles present or remaining, or not captured actually, or decreases. And you can see that our R squared is close to 1, which means that the variance is very good, very close to that. And now just for some overkill, we're just gonna go right here. They're like the qualitative evidence is that, as you can see here, there's a lot of little small particles and compared at 0 kilovolts per centimeter. And then going towards the end here, we have very few particles present. And then just now moving on to the conclusion, as we've seen, there was a 97.5% decrease in particles present. It was a very important thing to find out. And likewise, we were able to confirm that there was an inverse relationship between the number of particles not captured and the voltage, or the electric field that was created by the voltage. And another thing that was very good to see above all is that the electroradiology approach, or Dr. Tao's and his laboratory's method, can be very important in improving public health, the environment, and can be used to solve many other problems within our society. For future work, we still really need to kind of really focus on airflow, because we've seen that particles are really moving around we really just need to optimize airflow. And that's one of the things we really need to focus on in the future to improve and optimize particle capture by the electrodes. And lastly, I'd just like to thank Dr. Tao and Xiaozhong Zhu from the physics department at Temple. And I'd like to thank the NSF Foundation for giving me this grant, and for all the people that helped me out along this way. Thank you so much.
All right, thank you so much, Jonathan. At this point, I will take questions from the audience. Are there any questions? Any questions? Jonathan, I did have one. So the PM 2.5 pollution, because I'm not familiar with this is outside of my area, but what kind of a device would I find this pollution coming from?
Sure. Yeah, that's a very good question. So usually this is really a big threat to certain areas where there's a lot of factories. For example, if you like communities that live around very industrial sites, this would be something that's very something to keep in mind and very dangerous for just the health and the environment. So it's mainly just factories and anything like that. It's not really a thing that really emits a lot. Like, for example, like your cell phone, or like even your car. Like your car might be emitting some of it, but it might not be enough to really pose a threat, since it's kind of it's just like not as much compared to like a factory of making plastics, chemicals, and stuff like that. So
Yeah.
Yeah.
Thank you. Any questions from anyone else? All right, if there are no other questions, thank you so much, Jonathan, for your presentation. Very good job.
No
So
again,
there were some people that entered in afterwards, and we'll get ready. The next speaker can come up, Carol. But this session is being recorded and will be made available for viewing by next Wednesday. And again, if you have any questions for the presenter, I ask that you please put them in the discussion board. So at this time, we will move on to prayer review. So prayer review, Carol, are you ready?
Yes, I'm ready.
All righty. The floor is yours.
Okay, can you see everything?
We can.
Okay, great. So hello, everyone. My name is Carol Atkin, and I did my research under the supervision of Dr. Tapasan to create a wearable strain sensor compression sock for DVT prevention. Now, before I get started, I would like to tell you all about DVTs in order so that you better understand my design. So DVTs are deep vein thrombosis, which is a blood clot within the walls of your veins and arteries. And they become fully osculated, usually behind the calf of your legs, when thrombocytes build up and block the motion of blood going through your veins. So if you ever sit down for a long flight, maybe you're studying, maybe you have a desk job, or maybe you're just sitting down and watching Netflix and you're at a risk of getting a blood clot, especially if you don't move around and get up and walk. So in this case, I wanted to see how I can prevent DVT prevention at the partial oscillation stage, which is basically just half of a blockage, in a strain sensor that will be embedded within a compression sock. And compression socks, kind of like the one you can see here, that you can kind of see here. Compression socks are a form of blood clot prevention. They're designed to gently squeeze the legs more than typical socks to promote better circulation and thus can reduce the chance of DVT. So the partial oscillation stage is when thrombocytes build up and block half of the circumference of the vessel. I want my sensor to be able to detect abnormal blood pressure. Too much can indicate a force that is blocking the blood current. I also want to be able to check pulse oximetry and temperature to see if there's any alarming changes within the body. If it's too cold, for example, and if it's not due to the environment, that would definitely mean there is lack of blood flow. As an example, if you were to tie a rubber band on the tip of your finger, there would be a drop in the levels of oxygen and an increase in pressure from the blood that's trying to flow. And the reason that is because you're blocking the amount of oxygen and blood that should be going to the tip of your finger. And after a while, your finger will get cold and it will probably turn purple. And of course, leading after that, it will die off. Now, just think of this, if it was in your actual body. If this were to happen, death, unfortunately, will shortly come after. So all of these signs in the hospital are definitely monitored within a patient's health. And it's vital to take into consideration a person's height, age, genetic disorders, and history, because as we know, everyone's normal is not the same as everyone else's normal. So as you can see here in the middle, my design is the shape of a Band-Aid. And the reason why I did that is because if you're like me, you think of Band-Aids and think of healing. The best location for DVT prevention is the superficial femoral and popliteal veins of the thigh and posterior tibial and peroneal veins of your calves. To ensure that my strain sensor had the best elasticity to detect your body and vein movements, I created a graphene indigitated design layer with an RC circuit to ensure that my strain sensor had the best elasticity and stretchability. I also use parafilm, which is right here, and I use parafilm because of its waterproof and stretchability as well, and it's for supporting layers for the graphene. So far on my AutoCAD design, as you can see here, the entire thing came up to be about 1.5 inches long and about 4 inches wide. The graphene sensing iron, which is right over here, this is approximately 25.4 millimeters long and about 12.3 millimeters wide. So the graph that you see below here is actually the real results of the sensor that I created, monitoring the actions of a pinky finger in this case. And our variables, as you can see in this case, is time in seconds and the percent of capitance. When tested, the flexing of the pinky indicated a downward spike, as you can see here, in the capacitance value. In contrast, when relaxed, as you can see here, there was extreme advantage, and it's averaged around 0% capacitance. This means that there was no motion detected. The picture on the top right shows how it actually looks like. This is the wearable sensor. As you can see, it's nearly the size of a US quarter. Right below it shows how it would look like on a patient's leg. It would be sewn in a textile, interdigitated design into a compression sock. If this experiment was completed again, I would definitely consider working with cheaper materials and allowing patients to be able to see their and monitor their health within an app. Thank you for listening. And if you have any questions, please let me know.
All right. Thank you so much, Carol. Any questions? Any questions at all for Carol?
I have a question for Carol.
Yes, go for it.
For this type of deep vein thrombosis, are some people more likely at risk? Like usually if people are, let's say, maybe obese or like have heart disease, are they more likely at risk for this?
Yes. So compression socks are actually mostly used in hospital settings, mostly for people who are post-surgery. So that's just after recovering. Let's say they have heart surgery. That's something very drastic. So they would be on a bed rest order, which basically just means that they need to rest, and it's best not to over move, because if you keep moving so much, of course, your heart's going to keep pounding. And then if you just had surgery, that's obviously not good. So they usually give compression socks to people who are going to be sitting down for a long time. So if you're going to be moving around, then you don't need compression socks because of course, your blood will be moving. But if you're not, then it's best to wear compression socks. And of course, if you do weigh different pounds, or if you're, whatever the case may be, of course, there are different types of compression socks that could fit anyone, basically. So it's just like a sock, it'll go up knee high, and it's just to compress the sock or compress your leg.
All right, we'll have one more question. How do you compare your sensor to ultrasonic devices, which are already widely used in hospitals?
That's a good question. So the reason why mine is more different is because mine isn't mostly for people in the hospital, it's for everyone. So basically, like me, I study a lot, so I'm wearing compression socks all the time, mostly because my mother's in the health side, and she always tells me, wear your compression socks when you're studying, since I know I'm not going to be getting up. But the reason why this is different is because you can monitor it on your Apple or whatever device you have. And it doesn't just monitor blood pressure. It can also monitor temperature. It can also monitor pulse oximetry, which is basically just the amount of oxygen within certain regions of your body. So I think this one is more different than the hospital because it has more different measures that we can take of a certain person rather than just one thing.
All right. Well, thank you so much, Carol. We appreciate you, and great job on your research. Continued success.
Thank you.
All right. So again, we will get ready for our third presentation. Again, this is being recorded, and so it will be made available through the WOVA app by next Wednesday. And if you have any questions for presenters, I just ask that you would please put them in the chat window. So our third presenter is coming to us from Lewis University. Samuel, are you ready? Samuel? All right, maybe not. If that is the case, if Samuel comes in, we'll come back to him. So we'll move on to the next presenter. So we'll move on to Oklahoma State. So Mason, are you here?
Yes, I am.
All right. If you go ahead and share your presentation with us, we'd appreciate it.
All right, can you see this?
Yes, we can.
All right.
All right, the floor is yours.
Oh, sorry, there's an issue.
Oh, okay.
It was playing a recording.
I will say we can't hear your recording.
Okay, great. That's good. All right, so my name is Mason Eggermeyer, and I'm a researcher at Oklahoma State. And my lab is interested in investigating microplastic occurrence in Oklahoma fresh water. There's currently a lot of microplastic region, usually involving oceans, and So we were really invested in the local pollution of freshwater systems. So in order to identify some of the microplastics in fresh water, we needed to come up with a way to separate the plastics from the sediments. And you may have heard of Oklahoma red dirt, and Stillwater has a large amount of clay and silt in our soils. And so we had to work around this, and that was a big challenge in our research to actually extract the microplastics. So we decided to use a process known as elutriation, and that uses the density and settling velocities of soils and microplastics. And by exploiting the settling velocities, we can collect microplastics while separating the clay and silt. So we developed these continuous flow columns. There we have 3 here, and we use continuous flow because most microplastic research uses batch elutriation, which you just throw in the sample and let it run. But the clay and silt form plugs that collide with the microplastics, and it is a challenge to actually get any plastics out. And so our objective was to design the continuous flow process to actually extract microplastics. And so after designing these columns, we have a new process where you run the sample through the columns. It's pumped as a slurry into the column, and we collect the plastics in a sieve stack, with the smallest sieve being 45 micrometers. After that, we do density separation using a zinc chloride solution, which you can see here. And we withdraw the supernatant and then digest any organic matters, because our freshwaters usually have leaves and organisms. After the digestion, we then filter it over a 0.2 micron aluminum oxide filter. And then we then take the filters to the stereo microscope. And these images here, figure 5, are stereo microscope images of potential plastics, because we assume that all of the organic matter, such as leaves, have been digested away. And the heavier densities, particles such as soils and rocks, have all been settled out. So we have 2 different magnifications, and you can see some sort of threads and some perfectly round particles. It could be potential plastics. And in order to characterize these actually as plastics, we take it to the micro FTIR and use an ATR with a germanium tip to use infrared light to identify the unique spectrum of microplastics. And so figure 6 is the spectrum of the one plastic we've identified so far, a type of synthetic rubber. That may have, this sample was taken near a road, so maybe fragments of a tire or something. We can't really tell what plastic it is, but we've identified that as EPDM. So our primary conclusions are that microplastics are polluting Boomer Creek as it runs through Stillwater, Oklahoma. And we hope to further investigate the occurrence of plastics in other regions of Oklahoma, including Tulsa. And we hope to sample along different points to see how the types of plastics change as it moves through town. And so that goes into some more of our further research, where we will test different sample types of sediments, such as sand, or the eastern half of Oklahoma has less clay. So we'll test how the efficiency of our columns work to separate the plastics from the sediments. And that is it. So thanks for listening. Do we have any questions?
All right, any questions? If you have any, please put them in the chat. I know, Mason, you use FTIR to identify the plastic. So I was wondering what sort of controls that you use to know that the spectra you were looking at was a plastic and not a sand or something.
So we hope that through the density separation, we've extracted most of the sand. However, in my pictures, you can see that there's some particles. The FTIR usually gives us a match of what it actually is. So if we had if, for example, sand, the FDIR would report that as the sand. And so we had a match. That was a big issue and why we had to add the density separation step, because it kept identifying only the sand or as opposed to the microplastics.
Okay. Any other questions? Any questions? All right. If there are no other questions, thank you so much, Mason. Great job, great work, and continued success to you and your research.
All right, thank you.
Thank you. All right, so we will get ready for our second to last presentation today. Again, this session is being recorded and will be available through the WOBA app on next Wednesday. And if you have any questions, again, please put them into the chat. So we will now go to Lincoln University, where we have Davion, I believe.
Hello.
Hi.
Can you hear me fine?
We can. If you want to go ahead and share your screen.
Okay. Can everybody see everything okay?
It is coming through eventually. I don't see anything yet. There we go.
Okay.
Perfect. The floor is yours.
Okay. My name is Davion Washington. I was at Florida International University studying with Vladimir Pazin as my mentor, accompanied by Stacy Darpo as another one of my partners. My topic was flexible optical filters for health monitoring devices using pulse oximetry and fluorescence spectroscopy. On-body sensors enable continuous health monitoring and disease diagnosis. Pulse oximetry is a non-invasive optical technique used for optical measurements in arterial oxygen saturation and heart rate sensing. Fluorescence measurements enable optical measurements of tissue oxygen, lactate, glucose sensing, and urate sensing. We conducted research to understand the landscape of available optical measurements for wearable health monitoring and identify potential for flexible optical filters. Flexible filters materials were selected for commercially available organic semiconductor materials, which are typically used for organic light emitting diodes or organic thin field transistors. We found that for pulse oximetry, we found P3HT and PBD/TTPD best fit for pulse oximetry at a wavelength of 630 nanometers and 550 nanometers. And for fluorescence spectroscopy, we found that PBD/TTPD at 550 wavelength was best fit for phosphorescence. For our sample preparation, we cut glass slides into squares, 1 inch by 1 inch, and then we cleaned the squares with Halmanix 3, and then cleaned them with deionized water, and then we submerged them into the ultrasonic bath. We dried them with nitrogen gas, and then put them into the spin coater. We then put the solution onto the slides and then spin them. The samples were then put on the hot plate to then dissolve whatever material left. For our absorption measurements, we set up the Keysight machine. We placed alligator cables on the light, and then we put the 12 volt and 1 amp found in the A6 and started it. The exposure starts at 30 and the boxcar starts at 3. We turned on the LED. We turned off the LED. We got the background and subtracted it and turned the LED back on. We got the current spectra and placed the films and absorption measurements. Over here are our results for our PBD/TTPD, our PCPPM measurements. Both materials absorbing at a 650 wavelength, which is best fit for both phosphorescence and pulse oximetry. Over here, we can see the fluorescence measurements for PBD, triple TPD. The signal with the filter is a lot stronger than the signal with the filter, meaning that the signal with the filter is a lot stronger. I think in analyzing, we found that PBD, triple TPD, and P3HT are well suited for absorption. These materials exhibited large absorption coefficients and spectrums matching the requirements for pulse oximetry in the 550 nanometer wavelengths. PBD triple TPD demonstrated to have minimal autofluorescence and is well suited for 700 nanometer sensing in wearable devices. Environmental stability was mentioned under accelerated conditions. Here is a picture of the actual finished product of the actual filter that we used to absorb with LED. And that is all for my presentation. If you have any questions, I'm happy to answer anything. Thank you.
Thank you. Any questions for Davion? Any questions? And Davion, I'm not an engineer, so I'm not very familiar with this work, but I do know about pulse oximetry and pulse oximeters. But I guess my question is why develop a flexible filter for a pulse oximeter?
We developed a flexible one so we can, just like the I forgot what her name was, but she had the sock, the compression sock.
Mm-hmm.
We did one similar to that for the foot, so you can wear it and wear for longer periods of time and measure, get measurements over like courses of weeks and months, and then you have to wear it, and then it's like so it's more comfortable, I should say.
Right, something you can wear instead of the stiff
exactly
machine. You just put your finger in between. Okay.
Exactly.
Very good. Any other questions for Davion? All right, if there are no other questions, Davion, thank you so much for your work.
Thank you.
Continued success to you, and we look forward to seeing you in the future.
Thank you, I appreciate it.
Thank you. All right, so I was looking in the participants to see if Samuel has come, but I haven't seen him come yet. So we will continue to move on with the last speaker. So we will be going to Tyler, Texas, at the University of Texas. So is it Kiyoung?
Yes.
All right, awesome. And we can see your screen. So the floor is yours.
Thank you. Hello, everyone. I'm going to present Kirigami-inspired net-like graphene strain sensor for motion detection. Strain sensor means measure the deformation due to external forces. In this study, we developed a flexible and stretchable strain sensor with graphene, and also we introduced a Kirigami architecture to the sensor for adding resilience to accommodate the stress and strain caused by body movements. Therefore, let's look into graphene's attributes and Kirigami structure to help flexibility on a wearable strain sensor to record body signals in dynamic conditions. Graphene is two-dimensional crystal carbon structure in a hexagonal lattice. It is the thinnest material and incredibly strong, about 200 times stronger than steel, and it has 120% of stretchability. And also graphene is an excellent conductor of heat and electricity. In stress strain curve, zigzag horizontal direction has higher fracture point than armchair vertical direction. Zhao and Alulu's graph shows graphene's nominal strain versus stress under uniaxial tensor test along the armchair direction at various temperature in the 210 Journal of Applied Physics. On top of excellent properties of graphene's flexibility and stretchability, the introduction of kirigami architecture enhances and supports them. Kirigami is an art of cutting paper into three-dimensional shapes. And our strain sensor is inspired by this net-like kirigami architecture as shown in the slides. From this motif, 1 inch by ½ inch sample of diagonally oriented 0.6 millimeter by 0.6 millimeter width and depth net-like graphene strain sensor was developed in Dr. Sawana Tabasum's laboratory. About a quarter size, the graphene strain sensor was fabricated for the tensor test. For the experiment, we conducted a finite element analysis for the simulations and a tensor test for the actual experiment. When 1 Newton applied push and pull directions onto the sample, it deforms 0.00037 millimeter. Also, when 500 Newtons applied, likewise, it displaced 0.18 millimeter. Mechanical device stretched the sample with 3.045 e to the -8 Newtons, and graphene sample responded in linear fashion up to about 28% of breakpoint in tensor strain curve. This outcome exceeded 20% of elastic limit of graphene, general graphene's characteristics, and commensurate with the theoretical properties. In conclusion, in summary, the graphene is an excellent material for wearable strains and measurements, and kirigami-oriented net-like structure enhances the flexibility. For the future work, the research will be conducted on developing patches to record the wearer's pulse rates, chest rates, respiratory rates, and muscle movements. Also, project is going to be developed for sensing the detected data to the caregiver via cloud. The special thanks to my mentor, Dr. Sawana Tabasum's tremendous support, encouragement, and insight for this research project. And also thanks to HCC's Dr. Blackmon and Jeff Steers' support and opportunity for this summer internship opportunity. Do you have any questions?
All right, any questions? Thank you so much. I will say while we're waiting on some questions, I was going to ask you how was kirigami different from origami, but you said that kirigami is you're cutting into
Yes.
three-dimensional shape, whereas origami is folding into three-dimensional shape.
Exactly,
So
ma'am.
I was like, oh, okay, so that's the difference. All right, I got it. And I will tell you, you were talking as you're talking about the strength of this particular material and this structure. I'll be honest, I was thinking of the Black Panther there because I remember he had on some sort of a suit that had this ability to bounce things back or whatever. So that was pretty awesome, pretty cool. But I know yours is a little bit different. Now, in your study, I noticed that you talked about how you measured the stretch in the length. But I was wondering, did you also measure the stretch in width, since this particular material stretches two ways, as opposed to just
Yes,
one way.
yes, that's why we made this sample and design is a diagonally oriented. So
Oh, okay.
hover, armchair direction, and also the other direction. So
Gotcha.
it's like a plus minus
Mhm.
effect, and that it gives like an average the tensile structure. So that's why that's the key point of our design.
Awesome. All right. Any other questions? Any other questions? I just looked in the participants list and I did not see Samuel listed, but before I
Oh, I'm sorry.
assume that the case, are you there?
Yes, I am. I'm sorry.
Perfect.
It said on the listing that our session started at 2. I was somewhat confused. I'm sorry.
No worries, no worries. So let me, I need to see, let me find you in here because I don't think you have co-host. Let's see, how are you listed in here? Are you listed as Samuel?
I think listed as a pentane.
A painting. Oh, okay, I got you. I see it. Let me give you co-host, make you a co-host so you can share your screen. All right, perfect. So you should have the ability to share your screen now. For those who have joined us afterwards, just want to remind you that this session is being recorded and you will be able to view it via the WOVA app by sometime next Wednesday. And if you have any questions at all for any of our presenters, please put them into the chat. So while we're waiting on Samuel to come, I just want to say thank you so much for all of you who have attended. We've had some great speakers and great research presented thus far, and we look forward to Samuel's work as we go to Lewis University. So Samuel, if you're ready, the floor is yours. Oh, Samuel?
Yeah, I'm sorry. I just have to pull up my PowerPoint.
Oh, okay. It was up, but I didn't, unless it was a different one.
Okay, so for my research over the past summer, I worked at the engineering department at North Central College under Dr. Frank Harwath, and we researched material analysis of mud bricks, also known as adobe, with like the intention of replacing them with what we consider like traditional concrete bricks in construction. It's not widely known, but the heavy use of concrete and like the mass production across the entire world is essentially having knock-on effects on the climate and the environment. I found estimates that at least 5% of the world's global CO2 emissions are due to production of concrete. And then also another less known factor that's having negative effects on the environment is sand theft. The type of sand needed for concrete can only come from marine sand that's found near beaches. So you'll literally see people go up to beaches throughout a lot of developing nations and just steal sand from the beach, and it'll just completely destroy the local environment and the corals reefs there. So ultimately, we just try to like not only help the environment, but make the process of building buildings cheaper, because rather than having to invest in all the infrastructure to make concrete and the necessary requirements, you can literally hopefully build from dirt and material at the site of construction. So on my top left of my poster, you see examples of the Taos Pueblo and a mud brick in Syria. Both of these structures are well over 1,000 years old. So in the right environment, a mud brick can withstand the test of time. And a lot of our research is trying to figure out how our ancestors managed to build buildings that stand today. So I hypothesized that the type of bricks and the type of dirt they used to make the bricks were a concentration of highly pressurized brick with a lot of moisture content. So they really managed to squeeze a lot of material with a lot of water that would able to like make it sturdy comparable to concrete. And so alongside that, we altered the moisture content and the formation pressure and the cooking heat and how long we cooked it. And we compared the process of how it impacted topsoil and subsoil to see which of the two would actually be the best at making bricks for good comprehensive strength. After cooking, we crushed the samples in a compression force tester to analyze the compressive strength, which is how much force they can undergo before they are crushed through vertical force. And by placing the manipulated variables in the respective compressive strength in the factorial matrix, as you see in the middle on the far right. Yeah. So we essentially had all of our, because the thing is, you need to be able to test which material factor relates to each other and how they actually impact the compressive strength. So you need to put it in a factorial matrix that is able to isolate each variable. And as my professor told me, if we try to do it like in a traditional sense, we would have to be do the calculations for each one with a factor of 2 to the power of 6 or 8. Like, there's no reasonable amount of trials that you can do to actually get the amount of information you need. You have to put in a factorial matrix. And through that, we were able to find that my hypothesis was only partially correct. It turns out that pressure has nothing to do with how well a mud brick will perform. The two main factors is having a high moisture content and having the topsoil be able to absorb that moisture. As you can see in the prediction profile, the water percentage is the one that correlates highest alongside with the soil type. So both topsoil and high water content is what's needed to make a good brick. And when we were able to analyze our compressive strength, the highest batch we were able to produce averaged around 112 kilograms per centimeter squared. When compare that to high class bricks on like an international scale, that's performing higher than even what people buy at the highest rate to make their own buildings. First class bricks only have 105 kilograms per centimeter squared. So our best batch were able to outperform traditional concrete. So this result is very much positive. It only piques my interest more in this field of research because replacing concrete is such like a basic thing that we take for granted, but in doing so, we would probably revolutionize how we build our modern society. So I'd like to thank Dr. Harwood. Before that, I wanted to talk about possible avenues of research. So where we were going to go was to have different sealants protect the brick, because one of the big issues that concrete can withstand the test of time, because barely nothing can really scratch it over long periods of time. Exposure to acid rain can weaken concrete, but not as much as what it can do to organic material. And that's the big issue with topsoil, which performed the greatest. Another thing is that I want to figure out a way to replace the organic material in topsoil, because a lot of things is that we don't want to replace, not allow people to farm and take up all that necessary nutrients that are associated with farming to build houses. Ideally, we would try to find a binding agent that could be put in subsoil so that we can have both topsoil and the unnecessary subsoil that is in abundance that we don't use. So yeah, that's the results of my research. And I'd like to thank Dr. Harwood for his mentorship, and North Central College for having me. Also the Lewis Stokes Alliance of the LSMRCE Alliance, and that's my research. Thank you.
All right, thank you so much, Samuel. Very interesting work. Any questions for Samuel? Any questions? Well, I do have one or a couple of questions. You started off your talk stating that these mud bricks um, in the right environment could survive. And I guess I was wondering what was the right environment, or what does the right
So,
environment look like?
and that's another possible avenue for like control and research, because of Syria and the Southwest of America are characterized by dry weather and, not a lot of water exposure. And another thing is that the weather is incredibly predictable. So even if like over a long period of time, you can expect a certain amount of rainfall, as opposed to like in the Midwest, any other day could be like a couple inches of snow or whatever. And so when I say 1,000 years, it's important to acknowledge that Syria and Southwest have remained unchanged for essentially 1,000 years. So more research should be done to like how much the mud brick can actually withstand like frost, water erosion, acid erosion, and like frost erosion as well.
And then one other question I had, because it's very interesting to me, and I do understand the negative effects of concrete, but I was kind of wondering, what are your thoughts about a mixture of this mud and concrete in the making of bricks, such that you would use less concrete, but maybe incorporate this, especially considering the increase in strength that it provides?
That could be a possibility. I only would, and this is only my personal opinion, but I would focus on the mud brick specifically, because I'm of the opinion that it should be drastic in the sense that no sand would be required. Because me learning about essentially the non-renewable resource of sand, like kind of floored me. Like, oh wow, like sand is something you take for granted, but it takes thousands of years for rock and like marine life to make sand. And so the fact that people can just like take it and steal it, and it's essentially like oil, like it's going to go away soon. It's like, oh, I'm trying to see if we can make a substance that's independent of sand.
Got you. All right. Any other questions? Any other questions? Well, thank you so much, everyone, for being here. I am happy to report that we made it on time. So thank you again for all of you who have attended today's session. As a reminder, this session has been recorded and will be posted to the WOVA app by Wednesday of next week. So thank you so much again to all of the students and your work. You've got some excellent projects. I love just the novelty of it all and the creativity that's there. And so I wish you all the best and continued success, and enjoy the rest of the conference.
Thank you.
All right.
Thank you so much. Take care, everyone.
Thank you. That concludes this session for Group 4.